energy on the boat is plus the potential energy changes is equal to the work done on the boat. Now, if you drop, the work is not all done on the boat from the outside. It basically, there is free fall. So by doing this, there's an initial kinetic energy final, wherever it drops to, minus the kinetic energy minus UGI. Because there's no work being done on the system, on the boat, so by the isolated system is 0. If that's the case, then we have kinetic energy final plus UGF final equal to kinetic energy initial plus the UG initial. So look at it. This is associated with final. This is associated initial. That's considered as constant. This expression is very important for us. If you've written it out in this, that means initial kinetic, this is called kinetic energy plus potential energy equal to constant. Or we can use the other one, is called conservation of energy. In this case, we like to say conservation of mechanical energy. The total mechanical energy is constant. That means, but it can transfer between kinetic energy and potential energy. So the total mechanical energy is total equal to constant. In that case, is equal to kinetic energy plus potential energy. In which case, 1.5 mv squared is equal to constant. So this is under the gravitation laws of action. And ladies and gentlemen, there's a beautiful theory about this. That means conservation of energy. Now, so the people have a misconception, and that's the end of the world. No, you have to match with the reality. What you're going to do, you could take this conservation energy, take it to the laboratory, test out. And then after that is go to the nature to test out. And finally it worked. Then from there on is conservation and energy. Using example 7.1 to demonstrate that with the ball dropping and falling. Dropping, so something like this, it drops, and then calculating the potential energy and kinetic energy. Now, there's an example 7.2 is very important, but usually we don't demand our physics 31A student to understand that. But we're going to demanding Hadrian to understand that. Because example 7.2 is related to setting up stage. Because you need to, like Peter Pan flying, right? So how can you design the string to holding up the Peter Pan? Okay, how to do the what do you call that, to do a Superman? You know, this one is designing Superman. If you're looking at the diagram, is Superman custom and Superman doing on page 194. That means all those what we call the setting in the movie, a lot of physics calculation to do it. Especially nowadays, another movie called Atlanta. All those movie setting is because the invention of application of physics. And so I will be highly encouraging you guys if you can go into that field, because that's a very lucrative field. If you know how to setting the movie setting by using physics, competition, okay, and not too many people know physics. See? So then you got a job. Like the hologram thing is the same. My ex-boss working at Xerox, working on, he has been working on the, what they call the Star Wars thing. They keep asking. My boss's name is Grafton, David Grafton. He's very, very good on this kind of thing. So anyway, this is one way to talking about. Now on the conservation of energy. Now the next one we like to talk about is section 7.3. On the section 7.3 is a very important section. In this case is how and non-conservative force, conservative force. What is conservative force? Conservative force basically related to gravitation. Gravitation. Gravitational force. And what's the other force? Means spring force is conservative. So what is non-conservative? Non-conservative force, that means after you're against that force, and the force will be wasted. What is this? This is a frictional force. Frictional force. So you have to identify this in order to understand. So we like to using the spring as example. Okay, spring is in action. We done this. Okay, so here is the spring, and here is the object. So you have that. So here is the spring, and here's the object. So we force it now like this. We push this up and down, up and down. Now this is conservative force because spring is conservative and the gravitational force is conservative. So you like this up and down, conservative. Now, when you're doing this, the spring force is conservative, but the friction is not conservative. The friction means between this and the table is not conservative. So how you going to handle that? So first we push it is potential energy for the spring, and then have a motion in here. It means kinetic energy, and there's a force against it that we call frictional force. So now there's a non-conservative and conservative forces adding together. In this case, UK is equal to 1.5 kx squared. In here, kinetic energy is equal to, in which case, 1.5 mv squared. What happened to here? This is a force, is a dissipator. So this force is doing the work. So in this case, we like to say plus kinetic energy. So this is related to the conservative force and non-conservative force working together. So in this system, we like you to review. Before you're doing any homework, we like you to review example 7.1, 7.1, and then read example 7.3 and 7.4. Okay, so that will be doing very well, or in addition to that 7.5. Okay. So we would like you to study this in order to solving your problem in the chapter 7's homework. Chapter 6, 7 homework already assigned to you, right? So did anybody have that in the number? Is number 53, is that one? Mm-hmm. And then number 55, yeah, and then number 51, and then 48 and 49, right? Yeah. Okay. Now, among all that, okay, so the teachers already tell you the better test comes from. So you narrow your scope to study. So it will be a lot easier for you. Now, in the midterm, the second midterm will cover chapter 7, chapter 8, chapter 10, and chapter 11, and chapter 12. The most important chapter will be at least two problems, 2 questions is come out from chapter 10. Okay, and that's a very important one. So now let's take a break, and when we finish, when we come back, we will go to finish chapter 4 and go on to chapter 8. 1.4.